You won't believe what I just heard. They say, grow your own vegetables because you never know if the store-bought vegetables have received the drainage water all along to nourish this faster. First, it's gross. Second, we know nothing. So come with me and let's find out if that's really true. The story begins with a seed no bigger than a sesame grain, pale, flat, and almost unremarkable. Yet inside that tiny speck lies a genetic roadmap that determines everything from how spicy or sweet the pepper will be, to how thick its skin grows, to the exact shade of red it'll turn under the sun. All red peppers are actually green peppers at first. They're the same fruit, just at different stages of ripeness. The green pepper is the immature version. It turns yellow, orange, and then finally red as it ripens. That red color isn't just pretty, it's a sign of transformation. As the chlorophyll breaks down, sugars rise, and antioxidants like lycopene and capsanthin flood in, giving it that signature hue and sweet flavor. The Netherlands, with its limited land and cool climate, manages to grow tons of red peppers using high-tech hydroponic greenhouses systems where plants don't even touch soil. Now, peppers are greedy feeders. Their nutritional demand changes as they grow. Early stages need nitrogen for leaf development, mid-stage calls for potassium to boost fruiting, and late stage demands calcium for firmness and color intensity. Once they're cut from the stem, their internal sugar and pigment development stops completely. Farmers look for an 80 to 100% color change, meaning the fruit has transitioned fully from green to red with a uniform shine. Brix meters, those handheld refractometers you might have seen, are used to measure sweetness. A good red bell pepper should register a Brix value of around 7 to 9, signaling the right sugar level. The peppers tumble gently through rotating drums, rinsed multiple times. After washing, they pass under air knives, high-speed air blowers that remove excess moisture. In modern plants, grading is done by machines that can inspect up to 20 peppers per second using cameras and sensors. They analyze size, color, and surface defects. Based on data, robotic arms or pneumatic air puffs direct each pepper into its assigned chute. Grade A peppers often go to fresh packaging lines. Grade B and C are diverted for steamed, roasted, or diced processing. Before steaming, many factories perform a temperature shock step. Peppers are briefly submerged in cold water around 5 degrees Celsius to firm the skin and lock in color. It's one of the most fascinating transformations in the world of pepper processing, a method that combines chemistry and engineering. At first glance, boiling peppers might seem easier. Dump them in hot water, wait a few minutes, done. But there's a problem: boiling leaches away almost everything valuable in the pepper. Vitamin C, for instance, is extremely heat-sensitive and water-soluble. When peppers are boiled, up to 60% of that vitamin C disappears into the water. Steaming, on the other hand, cooks the peppers with moisture around them, not through them. There's no water contact, no leaching, and the temperature can be precisely controlled. The result? The skin loosens just enough to peel away easily, while the inner flesh softens without collapsing. The natural sugars caramelize ever so slightly, enhancing sweetness, while nutrients remain intact. First comes de-stemming and coring. High-speed rotary cutters slice off the stem caps while a cylindrical vacuum tool scoops out the seed core. The remaining cavity is flushed with water jets to ensure no seeds remain, because even a few stray seeds can create bitterness during storage. Typical steaming temperature? Around 95 to 98 degrees Celsius, depending on pepper thickness. Duration varies too. Small strips may need just 2 to 3 minutes, while thicker halves can take up to 8 minutes. Where did the ice cream sandwich even come from? Believe it or not, the very first known version popped up in New York City in the summer of 1899. Yes, it's that old. Street vendors, dressed in white aprons, sold slabs of vanilla ice cream pressed between two thin graham wafers for just a penny. No branding, no fancy packaging, just a cool, handheld treat to beat the heat. By the 1920s, rectangular chocolate cookies had replaced wafers, and the shape we all recognize today, flat, neat rectangles with creamy centers, began to dominate. Fast forward to today, and ice cream sandwiches have grown into a multi-billion-dollar industry. Factories around the world churn out millions of these treats every day. They're so popular that in the US alone, more than 200 million ice cream sandwiches are sold annually, making it one of the top-selling frozen novelties. The process begins not with ice cream, but with ingredients collection. Without milk, sugar, wheat, and cocoa, you simply can't make a sandwich. And the supply chain is global. Milk powder and cream often come from large dairy farms in the US, New Zealand, or parts of Europe where cows graze on lush pastures. Everything is carefully checked in quality control labs. Flour is tested for protein content, sugar is screened for particle size and purity, milk is analyzed for fat percentage, and cocoa is inspected for moisture levels. If even one ingredient doesn't meet the standard, it's rejected. Big factories can't risk producing millions of sandwiches with a flaw. The loss would be enormous. Factories actually store these ingredients differently depending on how they'll be used. The basic ingredients are milk, cream, sugar, and stabilizers. Factories often use skim milk powder instead of relying solely on fresh milk. Why? Because powder allows precise control over solids content, and it stores for months without spoiling. Fresh cream or condensed milk is then added back to adjust the fat level. For sandwich ice cream, fat content usually sits around 10%. Just enough for creaminess, but not so high that it oozes out when you bite into it. Factories don't make ice cream sandwiches one by one. They build them in synchronized flows where every cookie, every stream of ice cream, every wrapper has its place. The cooled chocolate biscuits that were stacked earlier are automatically loaded into hoppers. From there, robotic arms or vibrating feeders place them neatly onto moving conveyor belts. The line spaces them out in perfect intervals, one cookie every few inches, to match the timing of the ice cream deposit. Inside, the ice cream is kept at just the right serving temperature, around -5 degrees Celsius, and pushed through nozzles under high pressure. When the conveyor brings a cookie into position, the nozzle drops a perfectly measured slab of ice cream right on top. It's not scooped, it's extruded. The thickness of that ice cream block isn't random. Factories design it to be slightly thicker than the cookies combined, creating that signature bite where ice cream dominates but the cookies still frame it. Usually it's around 1.5 to 2 centimeters. Too thin, and customers feel cheated. Too thick, and it becomes difficult to bite through before the cookies break. By the time a sandwich reaches the supermarket freezer, it has survived a complex process. Baked cookies, frozen fillings, precision assembly, and all of that so you can peel back the wrapper in seconds and take a bite. Lotus didn't come from a multinational food lab like many other foods. It came from a family kitchen in Limbekke, a village in East Flanders, Belgium. And that's what we want to show you today. The year was 1932. The Boone brothers were bakers, running a modest business. Belgium already had a tradition of spiced cookies, speculus, tied to St. Nicholas Day celebrations. Those were dark, heavily spiced, and usually pressed into wooden molds. The Boone brothers wanted something different, lighter, more delicate. Something you could eat every day, not just once a year. Their experiments landed on a thin biscuit, caramelized at the edges, fragrant but not overwhelming. It was crunchy but not hard, sweet but balanced. Locals noticed. The cookie was perfect with a cup of coffee. It didn't need frosting or filling. The flavor was already complete. Lotus never shouts about its spice blend. You won't see big cinnamon sticks or clove buds plastered across the packaging. Yet every bite carries those notes, subtle, balanced, unmistakable. Once the sheet is ready, it meets the rotary cutter. As the dough passes underneath, the cutter does two things at once. The outer ring stamps the cookie outline, separating each piece. The inner emboss presses the lotus border and logo. It's branding. Yes, but it's also function. That raised border acts like a frame, strengthening the cookie edges so they don't break in packs. What looks decorative is actually structural. Dough at this point is soft enough to take detail, but firm enough to hold it. Factories track dough temperature carefully for this reason. Too warm, and the emboss blurs. Too cold, and it cracks. Operators know immediately by looking at the logo if the line is running right. The belts themselves are designed for this stage. Dough travels on a smooth belt, but just before cutting, anti-stick treatments prevent sticking. Some plants use flour dusters, others a fine mist of oil. Every measure is about efficiency. You don't want dough sticking to cutters or logos coming out faint. Even if a single cookie got stuck onto the cutters, the entire batch will be a mess. Can you imagine? In warm seasons, dough sheets faster but softens too quickly. In winter, it stiffens and may crack. Factories control ambient climate with HVAC systems, keeping dough rooms within tight limits. That way the emboss looks identical in July and in January. Really? You didn't know that before? Let's talk numbers. A single rotary cutter can stamp out tens of thousands of cookies per hour. The line may run 24/7, producing millions per day. Every cookie has the same thickness, the same border, the same word pressed in the center. Well, that's more in order than my entire life. Cookies and crackers now meet the next stage. Not a small oven, not even a single chamber. These are giants, steel tunnels stretching 60 to 100 meters, wide enough to carry rows of cookies by the thousands. The belt is usually a wire mesh, open enough to let hot air flow through, but sturdy enough to keep cookies aligned. Once the dough enters, it will travel for 5 to 8 minutes, passing through carefully controlled zones of heat. The cookies are cool, golden, crisp, stable. Now comes the stage that decides if they survive the next 6 months of shipping, storage, and handling. All of this happens at astonishing speed. A single packaging line can wrap hundreds of packs per minute. That's how organized and well thought a good factory is. You can't underestimate their production. It is running at speeds far beyond our imagination. There's a comfort in heat you can control. A few drops, a small burn, a bigger smile. There's no condiment with more character than hot sauce. It's the little glass bottle that waits quietly on the table until you shake it. Then suddenly everything changes. Hot sauce wakes fries, hugs tacos, and brightens eggs. You know the red cap and the rooster. You know the diamond label that flashes Tabasco on glass. So how does raw peppers turn into glossy, tangy fire in a bottle? Is it just the pepper? What's that fire in its every drop? Let's shake it. Every bottle of hot sauce begins with peppers, and the fields that grow them are nothing like the produce aisle at your grocery store. Supermarket peppers are bred for looks, shiny skin, big size, and long shelf life. Hot sauce peppers are bred for work. They're chosen for consistency in size, strong flavor, and reliable heat. Factories can't afford surprises. One pod that's too big could jam a grinder, and one that's too soft might rot before it even hits the mash tanks. So farmers focus on uniformity because uniformity keeps the machines happy. Harvest is one of the most important steps. Cayenne peppers turn a deep, even red at ripeness. Jalapenos are picked glossy green for certain sauces or left to ripen red for sweeter heat. Habaneros glow orange like little lanterns when they're ready. Workers usually pick at dawn when fruit is cool and firm. Cool fruit bruises less, and bruises turn into soft spots on the factory line. A single acre of peppers can produce up to 20 tons in a good season. Those tons get loaded into bins, each one labeled with the field, block, and harvest date. That way, if something tastes different later, the factory can trace it back to the exact plot it came from. When trucks deliver the pepper bins to the factory, the real transformation begins. Before any grinding, the peppers have to be cleaned and trimmed, and this stage is as much about food safety as it is about efficiency. Think about it. Peppers come straight from soil, rain, and open air. They carry dust, microbes, and the occasional leaf or stone. For a factory producing hundreds of thousands of bottles a day, skipping a thorough cleaning step would be unthinkable. So the first stop is always the wash line. Pepper sauce in bottles shows up in 1877 in the United States. In 1868, Edmund McIlhenny ships a vinegar pepper blend from Avery Island in little glass bottles. The modern leap arrives with stainless grinders and pasteurizers by the mid-90s. Automation locks flavor and safety, and the world starts to stock heat. Formulas, though, stay behind locked doors. Some factories split spice blending across vendors. No single supplier holds the full mix. Machine settings live behind passwords. Only 2 people know the final ratio. When the mash flows from grinders into massive tanks, it doesn't look appetizing yet. It's chunky, raw, and sharp on the nose. But once you lock it away with salt, something remarkable begins. Factories often use stainless steel tanks that hold around 50,000 gallons. Older brands still cling to tradition and age mash in oak barrels, sealed tight with salt piled on top like a crust. Inside, natural lactic acid bacteria wake up. They eat sugars in the peppers and release acid. Over weeks, sometimes months, the raw burn softens into a tangy, complex flavor. You know, one Louisiana brand actually drills small holes into barrels, draws out a sample with a hollow tube, then reseals it with oak plugs and wax. Workers joke that the barrels look like they've been through woodpecker season. Fermentation also changes color. Bright red cayenne mash turns darker, closer to brick. If you've seen sauces that are brighter or duller, it's not food coloring, it's often the length of fermentation. Short ferments keep the color lively. Long ones deepen it. Acidity is a built-in safety system. As the pH drops below 4.0, harmful bacteria can't survive. This is why a bottle of hot sauce can sit on your shelf for 2 years without refrigeration and still taste fresh. To keep flavor steady, factories blend peppers from different regions. One year, Mexico might produce milder cayennes. Another year, California's crop runs hotter. By blending, factories keep your bottle tasting exactly like last year's, no matter what nature threw at the farm. Before bottling, sauce must be cooked and stabilized. After peppers are ground and fermented, the mash blends with vinegar and salt, then heats in steam-jacketed kettles. And you have already seen how they add the natural ingredients for perfect flavoring. Most people think pepper seeds carry the heat, but that's not true. The real burn lives in the placenta, the white pith inside the pepper walls. Capsaicin is produced there and spreads to the surrounding flesh. Seeds only taste hot because they touch this tissue. For sauce makers, grinding peppers whole captures maximum heat, but it also means seeds end up in the mash. That's why later processing stages need sieves and homogenizers to smooth out texture.
You never ever thought that how on earth does that tough bark become this soft and paper-thin tissue? Dude, this video is full of surprises then. When it comes to making tissue paper, not just any tree will do. For good quality tissue papers, they need to rely on softwood and a little hardwood trees, but majorly eucalyptus, pine, and spruce, because it's all about the fibers. These trees grow in managed plantations, and an eucalyptus tree can be ready for harvest in just 7 years, compared to pines, which take around 20 to 30 years. These machines can grab, cut, and stack a tree in seconds, making the process incredibly fast. Once the logs arrive at the pulp mill, they immediately get debarking and chipping, which means the very first step is removing the bark. These machines reduce entire logs into tiny uniform wood chips in seconds. Now the wood chips are fed into a massive pressurized tank called a digester, where they are cooked in a cocktail of chemicals, mainly sodium hydroxide and sodium sulfide. This mix is known as the Kraft process, and its job is to dissolve lignin, the natural glue that holds wood fibers together. Once the pulp is freed from the wood chips, it needs to be washed and bleached to remove any leftover lignin and give it that bright, clean look. So that dull brown color changes into the white mesh. What's actually happening inside? Each fiber is being gently pulled apart, shortened, and fluffed up. Before this soupy, fiber-rich mixture can become the soft tissue we use every day, it needs to go through an in-depth transformation. It all comes down to refining, a process that carefully breaks down and reshapes the fibers to create the perfect balance of softness, strength, and absorbency. This makes the tissue feel softer, more flexible, and, just as importantly, more absorbent. At this point, it's still about 99% water and only 1% fiber, which means it has to go through a serious drying process. As the pulp spreads out on the mesh, water immediately starts draining through the tiny holes, leaving behind a thin, even layer of wet fibers. If the fibers aren't evenly distributed, the final tissue will have weak spots or tear too easily. This is where the last bits of moisture rapidly evaporate, taking the tissue from a wet, flimsy sheet to a dry, structured one. One step that is performed at this stage is called perforation. It is what creates the tear-off sections you see on toilet paper and paper towels. The jumbo rolls arrive at the converting factory, where they are rolled onto the processing line to cut them into easy-to-drag bundles. These tissue rolls also pass through a set of engraved metal rollers, which press a pattern into the layers. Embossing actually helps trap air between the layers, making the tissue feel thicker and softer without adding extra material. This is how some brands create ultra-soft tissue without making the rolls physically bigger. Here, they get ready for the factory packaging, and these bundles will be transformed into stacked bundles that are actually pretty practical for monthly usage. Now that the tissue is perforated and embossed, it needs to be rolled back up into log rolls, which is a common version of a regular toilet paper roll, just a few meters long. The rewinding machine tightly winds the tissue sheets around a cardboard core. This core is what gives the roll structure and keeps it from collapsing when used. Some brands skip the core entirely, creating coreless toilet paper rolls that can hold more sheets in the same space. These are common in commercial and eco-friendly products, reducing waste from empty cardboard tubes. Not all tissue rolls are created equal. Ever wondered why some toilet paper feels super soft and fluffy, while others feel rough and cheap? It's all about fiber selection. Premium toilet paper uses longer, higher quality fibers, often from eucalyptus trees, because their fibers are naturally soft and strong. While cheaper toilet paper uses a mix of recycled fibers, which are shorter and don't bind as well, making the tissue feel rougher. Unlike tissue rolls, which are tightly wound and perforated, tissue sheets go through a different process to become facial tissues, napkins, or handkerchiefs. These products need to be soft, neatly folded, and easy to pull out one at a time